Hi everyone, this video is about the last of the 4 lessons on energy, specifically in the particles and energy scheme of work. And really this is the concept that we will keep coming back to in physics throughout students' journey into Key Stage 4 and Key Stage 5 as well. And we all know, as science teachers, conservation of energy is a super important topic. But it sometimes feels so fundamental that it's actually quite difficult to teach. So quite often, we'll give students a definition and we'll say, well, energy can be transferred, or maybe it's dissipated, and we question them about what those words mean. But we somehow feel like we've not really got the depth and the importance of this idea across. And what I would say in this video, and when you're preparing to teach this lesson, is actually it isn't that complicated given the work we've already done in the previous 3 lessons, in that really all we're doing when we say that energy is conserved is saying, well, given all of the diagrams that we've drawn so far and how we've laid it out and how we've thought about the different energy transfers, different energy stores, whether it's useful or wasted and so on, all we need to do is put an equal sign in there and say the numbers before the event that go in are equal to the numbers after the event that goes out. Really, that's it. It's just saying if we start with a certain amount of energy in the bank, so to speak, to use the money analogy, then when we spend that energy, when we actually use it to do something, we can't get any more, and we're not going to end up with any less. It's going to be transferred somewhere, or it's going to be dissipated to the surroundings. So I've spoken a lot there. I would suggest when you do this with students, again, the lesson is an I do, we do, you do structure. Just get straight into it, and actually they will get the concept even if they don't have a really strict definition. But for the sake of Key Stage 4 and Key Stage 5 physics, that's really all we want. So the first example in the slides is a toaster. I'm going to draw my toaster like this. I might show that it's plugged into the wall again, like that. And again, a bit of questioning. I can't remember whether this is in the low stakes quiz. It might be worth putting this in the low stakes quiz. But just a reminder that here the useful energy is heating the toast. But you might want to add something like this, that there's some energy wasted by heating the surroundings. And all I'm going to do is draw my same type of diagram that I've been doing in the previous 2 lessons. So I've got an electrical transfer in. My useful energy transfer out is heating, in this case toast. That's going to increase the thermal energy store of the toast. Just a reminder, I don't put an energy store at the beginning because it's plugged into the mains. If this was from a battery, that would be chemical energy from the battery, but I don't know where it's come from, so I'm just going to leave it blank. And then energy is wasted, again by heating, this time by heating the surroundings. And as I said in a previous video, students may question you on things like, they often think about sound with kettles or whatever. In this case, they might say, oh, well, what about the light? The amount of energy wasted by radiation is absolutely tiny compared to the amount of energy wasted by heating the surroundings. So, yeah, this energy transfer diagram is more than adequate for what we're looking at today. And as I hope you're seeing in these lessons, we start by doing exactly what we did before. And, if you wanted to do this on whiteboards, that would be fine because it's no different to what students have done in the previous lesson. All I'm going to do in this case is use the numbers from the worked example, which said, well, okay, if 100 joules of energy was transferred in. Now, I'm going to use joules here. You can just say that capital J, it just stands for the measure of energy, a bit like we have, pounds to measure the amount of money we have. I don't want to go down, when I'm teaching year 7, I don't want to go down the road of units and worrying about that too much. But we'll put it there anyway, just to be correct. But really at this stage it's about the numbers and them seeing the numbers balance on either side. But anyway, so I'm going to say 100 joules of energy is transferred in, and I can explain that to students. 10 joules of energy is transferred usefully. Now, we always draw a diagram so that the useful energy transfer is at the top. So I'm going to write 10 joules here. And then it says how much energy is wasted. And I can almost guarantee that any level of prior attainment, the students in your class will be able to tell you it's 90 joules. And if they can, then effectively they get conservation of energy. It really is that simple when you've laid it out in this really methodical way. Now, I would probably model the calculation here, but I mean, it's as simple as saying, well, okay, 100 in is equal to 10 joules plus question mark, and then just a little bit of rearranging says, well, the question mark is just going to be equal to 90 joules. And again, you don't even need to really model that. They'll be able to work that out by themselves. But it's good to go through it and just show that really methodical layout. So then the next example is very similar to this. It is to do with a light bulb again. So I'm not going to draw the light bulb just for the sake of time in this video, but you can sketch it out if you want. What is important though is that you draw the energy transfer diagram. So again, I'd probably get them to do this on whiteboards actually. And my guess is, because it's another very similar example, they'll probably get this right. What I would insist on when they're doing this on whiteboards is that they draw the energy transfer diagram, because that's going to be really important later on. So you want them to show that you've got this electrical transfer in. The useful energy is going to be radiation. And this is really important because when they come to putting the numbers in the right place, they need to be really, really clear what's useful, what's wasted. And in this case, it's heating the surroundings again. And in this example, for the sake of this video, I'm not going to do the whole thing. But again, the numbers here in that worked example number 2, it says, well, there's 120 joules transferred in. And 75 joules are transferred to heating the surroundings. And this is why it's really, really important that they're thinking here and not just blindly putting numbers in, because they need to make sure that that 75 goes here. And they do need to be really, really clear on whether the number goes here, here, or here. And it's worth you really probing them and checking them to make sure that they know what they're doing and why. So 75 joules here. And then the question is, how much is transferred out as radiation, or perhaps usefully, I can't remember. And again, we've got a question mark here, and you can do the same calculation. So 120 joules. And again, I would always model this because you want to go through that really methodical step-by-step and show how you move from the diagram here, so energy in, useful, wasted, to the maths. So in this case, it's going to be different because I'm going to put 120 equals question mark plus 75. And really being methodical about that and narrating that thought process is really going to help them make sure they get this right, as you'll see in the next example. And then you would get an answer of, what's that, 45 joules. Now, many of them will write that down straight away, which is kind of fine, but as you'll see in the next example, it's much better if they're really thinking about it and following your process. And you can show that by saying, okay, great, you've done that example, really easy. Let's have a look at the next example. So this is an electric fan, and it says 12 joules is transferred mechanically to move the air, 18 joules is transferred heat in the surroundings. How much is transferred in electrically? Now you've got the numbers 12 and 18 here. I can guarantee more than half, no, I can't guarantee more than half. I would be willing to bet that more than half of your students will write 6 on their whiteboards, because in the previous 2 examples, we've just subtracted the smaller number from the bigger number. They're going to think, great, I'll do that again. And this is why it's good to get them to do it on whiteboards and then say, okay, let's go back to the visualizer and have a look. So then I go back under my visualizer, I'll draw it out like this. So it was an electric fan. Got some energy coming in from some sort of store electrically. So then I'd get them to think, well, okay, what what is the useful energy transfer out of an electric fan? Well, in this case, it's moving the air. So if it's moving something, well, that's going to be a mechanical energy transfer. And how is energy going to be wasted? Well, as always, with all of these things, it's by heating the surroundings. So I'll just put heating here like this. And again, you can add the energy store if you want. So let's put thermal of the surroundings, just to remind them how we lay this out. And actually, in this case, sorry, I should have put it's mechanical transfer of energy, which increases the kinetic energy store. You could say the blades of the fan, or maybe we'll just put the air like that. Either is fine. Now, the really important part here is that you go through methodically the language in that worked example number 3 and say, well, okay, I've got 12 joules of energy transferred mechanically to move the air. And if you've gone through this process and really taken your time thinking about it, they will realize that that is the useful energy transfer out. So 12 joules needs to go here, like this. It then says 18 joules is transferred to heat the surroundings. So 18, well, that's clearly the heat in the surroundings. That's the wasted energy. That's going to go here. And then it says how much not how much electrical energy, how much energy is transferred in electrically. Now, once you've drawn it like this, they'll all be able to tell you straight away on their whiteboards it's 30. But again, this is why it's really important that you model that same process again and again to really get them thinking and being specific about what they put in. So again, what I would model here, just to finish off, is that question mark, this time, I'm going to put that as the question mark equals 12 joules plus 18 joules, and that's equal to, question mark, equal to 30 joules. Now, I think once you've been through those 3 examples, they're ready to do some deliberate practice, and there are 6 further examples that they can have a look at. Watch out for number 3 in those further examples, because that's another one like this. The only other thing students sometimes struggle with, I think it's question number 4, where there's more than one form of wasted energy. And again, all their diagram would look like in that case, it would be exactly the same. It would just look like this. So it would go energy in like that, useful out, and then you've got 2 wasted out like that. And again, if you just get them drawing those exact same diagrams, then they shouldn't find this hard. But actually, it's a really nice way of explaining this really profound idea that energy is conserved. So I hope that's useful. We've kind of finished the energy part of the particles and energy bit in these last 4 videos. What we're going to move on to next is looking at matter and the particles themselves in a lesson on solids, liquids and gases.